So as I said, what is Grover's algorithm? This is Love Grover. He found this in 1996. It's actually after Shor's factoring algorithm. It's a quantum algorithm that solves, well, I said it. It's a quantum algorithm solving this SAT problem. As we'll say, it's this unique SAT search problem. But they're all equivalent, and we'll see eventually how to solve the fully general set. In time, that's, well, it's basically square root 2 to the n. Okay, maybe like this, there's maybe this feature. I think it's like order m plus n times square root 2 to the n. I guess, by the way, square root 2 to the n is the same as square root 2 to the n, which is, about 1.41 to the n. So the sad take on this is like, well, it's still exponential time. Like, you still can't plug in n equals 1,000, let alone 1,000,000. But maybe 32 is better. So that's the sad take. The happy take is like, well, you could say, well, it's exponentially faster than our best known classical algorithm. It's faster by a factor of square root 2 to the n, so that's pretty awesome. So maybe, like, if n is 100, this is infeasible, but, like, this is feasible. Maybe, if you build your quantum computers. Or, from a more theoretical mindset, you could say, it breaks this hypothesis in the sense that, like, this hypothesis can only be about classical computers. So this is a belief hypothesis about classical computers, and quantum computers breaks it by a lot. So it really shows, at least if you believe this, that quantum computers are somehow more powerful than classical computers. Okay, so now we're gonna do it. Okay, so now we're going to start giving Grover's algorithm for this problem. And the first thing we're going to do is, the input is this code C. It computes some Boolean function f. The first thing we're going to do is what we always do. We're going to, like, convert C to quantum code so that we get if f then minus in our back pocket. Okay, so that's no problem. So, okay, we're going to start out by, like, get or make the if f then minus code. And we're going to kind of think about this. This is a unitary. If we think about it all together, this is a unitary operating in 2 to the n dimensions. Okay, so this is a d-dimensional unitary where d is 2 to the n. Somehow the number 2 to the n is going to come up a lot, so I'm going to call it capital D, because it's also the dimension. So this code that we built, from C, we really don't know how C works. So that means this code, even though we can run it, is sort of a mystery to us. But it's some kind of unitary, like rotation or reflection, in D dimensions. And we're kind of trying to figure out what it is. If you think about it, it's kind of like a reflection through the plane orthogonal to the sort of secret string ket x star. And we're trying to figure out what is ket x star. Okay. So yeah, let's think about it as, an operation on d-dimensional vectors. And again, we know, like, it breaks down into, like, 2D planes of rotation, which there aren't any, and dimensions of negation. There is one dimension of negation. It has one dimension of negation, which is the x star direction. And it's like no ops in every other direction. all other d minus 1 dimensions. Okay, so, how does it operate on a state vector? A state vector is like some extremely tall vector here of dimension capital D. And maybe its amplitudes are like A, B. This is kind of funny to call them like this. I don't know, P, Q, I don't know, Z or something. But anyway, there's capital D amplitudes. And this looks like a very minor operation. All it does is it like negates one entry, A, B, dot, 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 P, negative Q, R, dot, 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 Z. Okay, so remember, like, when you write n-qubit state as like a really tall column vector, like each entry is like named after a string. This is the ket all zeros entry. This is 0, dot, 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 1. And then this is like the x star entry. Okay, so this instruction we can build just negates one single coordinate, but we're like, but which coordinate out of the capital D? Okay, so it's like reflection through the d minus 1 dimensional plane perpendicular to this ket x star. And again, ket x star is this like really tall vector that's almost all zeros, except it's got a single 1. Okay, and that's in the sort of x star row. Okay, and by the way, I mean, if you remember way back at the beginning of the class, I talked about reflection across a vector. That's not this. This is the sort of the opposite kind. This is reflection across a plane that's perpendicular to a vector. Okay. Good. So we can make this code. And you might say, like, well, I don't know, how are we going to discover Grover's algorithm? You might say, I don't know, like, it seemed kind of similar to bias busting. Like, let's just start the bias busting code and see how things are going after a while. That's like an idea we can try. So let's try that. Where's good old black? Well, anyway. Okay, so we'll try this code. Let's try new qubit B1 through Bn. And then we'll do Hadamard all. I guess in bias busting we called this add and diff all, but it's going to be nice to work with normalized states, so we'll just use normalized states here. This, I mean, starts us in the state all zeros. And then, bias busting did if B1, FB1 through Bn, then minus. And then, well, let's just stop there and see what we'll do soon. Actually, we should have the prize pantry drawing. I almost forgot. We almost missed it last time. Let's go on pause here. We got the tickets? I'll grab them from you. It's a 1 in 5 chance today, if I'm not mistaken. It seems so long ago. It's hard to remember. Pretty sure it's 1 in 5 chance. I got a couple new prizes as well. Okay, sad. Let's go back to coding. Okay, so let's try to understand the geometric viewpoint of what's happening so far here. Okay, so the initial state after line 1 is all zeros. After line 1, it's all zeros, ket all zeros, which, if you think about it as an extremely tall vector, is like 1, 0, 0, 0, 0, dot, 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 0. Okay? And the height is capital D. And, okay, what about after line 2? Okay, well, the purpose of doing the Hadamard all, or the add and diff all, is to make the uniform superposition, the one that has equal amplitude on all 2 to the n, or all d entries. So if we were still using unnormalized states, that would have like amplitude 1 on everything. But it's going to be nice for us geometrically to work with normalized states. So we really should save those square root of 1 over 2 to the n here. But let's call this square root of 1 over d, because we're going to get used to saying capital D for 2 to the n. And I'll call this vector, this state vector, ket unif, because it's the normalized uniform superposition state. Okay, so after line 1, we're at this vector. After line 2, we're at this vector. Okay, so what about after line 3? Well, it's not too hard to understand. This is what if f then minus does. It just negates a single coordinate. So it takes the uniform vector and changes one of those 1s to a minus 1. So let's do this. So after 3, we get to, we still have the square root 1 over d times, it's terrible, 1, 1, and then there's like one negative 1 somewhere. Everything else is 1. Okay, and this negative 1 is, of course, in the x starth coordinate. And I'm going to abuse notation here. It's a little bit cheeky, but I'm going to call this ket f. Okay, because this is sort of like the plus or minus 1 truth table of f. It's 0 everywhere, which gets converted to 1s, except that it's 1 in this unique place, so that gets converted to a minus 1. Okay. So now we're at the sort of now what stage. So now what? Well, let's stall a little bit. There's my black markers. Let's first observe that these two state vectors after line 2 and line 3 are extremely close. They're almost the same vector. I mean, they only differ in one coordinate. So in fact, let's work that out. Let's look at unif minus f. Now, these are all state vectors. They're all unit length vectors. This difference is not going to be. It's going to be an extremely tiny vector. But I just nevertheless want to consider it. So what does it look like? Well, this scalar square root 1 over d can stay. And then it's actually 0 in almost all entries, except the x star entry, where it's 2. Right. Okay, so that's an extremely short vector, by the way, because this vector, x star, it's, well, there it is. It's a vector of length 1. It's a basis vector, but this gets multiplied by square root 1 over capital D, and capital D is truly enormous. So this is an extremely short vector. In fact, I want to make a couple of takeaways here that are kind of important. First of all, this difference vector is very short. It has length 2 over root D. Okay? And I'm going to draw a picture in a second. And this one is also very important. So unif is this vector kind of pointing in the all ones direction. We kind of know about it. We made it ourselves. It's pointing in some direction into space. Ket f is some extremely close by vector. We kind of don't really know where it is because we don't know what is this x star coordinate. So it's some like nearby vector. Now, think about these are not parallel vectors. So think about, these are two vectors in high dimensional space. There's some two-dimensional plane that they lie in, their span, if you will. There's some two-dimensional plane in space containing this vector and this vector. I'll draw a picture of it in a second. And what I want to claim is it also contains x star, ket x star. So why is that? Yeah? Yeah, this exactly says that x star is, square root d times the difference. So it's a linear combination of these two. So perfect. So that's very intriguing because we started with this vector, then we kind of made this vector, and we kind of know that this most special vector is also in this two-dimensional plane. So there's a lot of action in this two-dimensional plane. It's an extremely important plane to consider. So let's draw a picture of it. We're going to need this in a section. So remember it. If you want to reflect across your favorite vector v, as long as it's easy to code up v, then you can do it. Okay, so let's draw a picture of this situation. So there's this two-dimensional plane in d dimensions. We kind of know one vector in it. Like mentally, we kind of know uniform vector, and it's in there. We really don't know the other vector, ket f. But we know this is like in a very exciting two-dimensional space. So somewhere is this like 2D plane in, d-dimensional space. This is the circle of unit vectors. And unif is somewhere in here. Now I'm going to draw it horizontally, but that's just because I got to draw it somewhere. Don't take that too seriously, but this is unif. And on the other hand, ket f is also in this plane. And it's very close to unif, so let's draw it like pretty close. I mean, it's actually like microscopically close, but I don't want to draw it that way because then we wouldn't be able to understand our diagram. So let me draw it like here. But you should really think it's like truly microscopically close. Ket f. And I'm also going to like mark theta as the angle in here, because this angle is going to be kind of important. I forgot this takeaway. It's that x star is in the 2D plane of unif and f. Okay. So actually, let's draw the difference vector as well. We computed this difference vector up here, unif minus f. That's this. Oh gosh, I really should have drawn a more accurate picture. Okay. Okay, that green vector is the difference vector. And we know its exact length. The exact length of this green vector is 2 over root d. And remember, d is really large, so this is really small. So another thing I want to say is, well, theta is also extremely close to 2 over root d. Remember, what is theta? It's an angle, but angles are in radians. And what is how many radians is theta? It's literally the length of the circular arc here. That's literally theta. But this circular arc is like indistinguishable practically from the straight line arc, because this angle is so small. So like theta is maybe like minusculely larger than 2 over root d, but it's basically 2 over root d. Does that make sense? Okay. And finally, not only is this of length 2 over root d, this is literally 2 over root d times ket x star. So ket x star is in the same direction as the green vector, just length 1. So I'm going to draw ket x star in this diagram as well. It's the same direction as the green vector. So it's like very slightly tilted away from vertical, and it's unit. So it's like this. That's the difference vector scaled, so that's ket x star. Okay, any questions about this picture?